Welcome everyone. You are getting this video link because you emailed me saying you had a question on question number 2 on lack of conservation 2. I'm going to kind of set up 2A and 2B, and if you specifically want only B, I'll send you the direct link that will get you to part B. But so for question 2A, the idea is we have a box, 4 kilograms, that is pressed up against a spring. Okay, so there's going to be a spring. Now, the reason there's a spring is there's going to be some PEE. That's just kind of something to keep in mind. So let's just quick deal with forces. There is some forces. There is a gravitational force. There is a normal force. There is a force of friction, because once we release the spring, the object's displacement is going to be going that way, so therefore friction is going to be acting this way. The coefficient of friction is 0.70. Okay? Now ultimately what we're asking you to do is solve for how far does it go that way. So it says that initially it's being held up against the spring, so it's going to start at rest, and then it's going to end up over here somewhere. We don't know how far, right? That's the question mark, until it comes to a stop. So over here, we have a compressed spring. So we're gonna have K1, we're gonna have X1. Our K is 2,000 newtons per meter, and that spring is compressed 0.3 meters. And we're gonna hold it, and then we're gonna release it, and it's gonna go that way somewhere. Now, eventually what you're going to do is you are going to use this equation. Let me just make sure that's still in the shot. We're good. Okay. So again, starts at rest, ends at rest. We have some things we can cancel out. Horizontal surface has some stuff we can cancel out. At this location, we have a compressed spring, but over here, there's no longer a compressed spring. There's some confusion that we get sometimes saying, is there any work in? Is there an applied force? And the answer is there is no applied force stated, therefore there's no work in. There is friction though. Okay, so in order for us to solve for this, we are going to solve for that delta x in our work done by friction equation. We are going to solve for this delta x in this equation. So how do we do that? Well, we solve for work done by friction here first, then once we get a number, we are going to plug it in to here. Now remember, work done by friction, we need the force of friction first. So we're going to have to do some forces stuff up there. But then once we get that number there, we can solve for delta x. That's how you set up part A. If you still don't understand, email me again and we can try to set something up to kind of discuss it, or I can try to address that a little bit differently. That's part A. Part B. Okay, part B is similar in the sense of we have some of the same starting conditions that we had for part A. It's still initial velocity is 0. There's still 4 kilograms. There's still gravitational force, normal force, force of friction. My force of friction is going to be the same because my normal force and coefficient of friction is the same. I'm still going to have a compressed spring at location 1. But now what's going to happen is it has not, I think the work done by friction here was 90. I think it was 90. For part B, the work done by friction is not going to be 90. And the reason it's not going to be 90 is because when we say work done by friction is equal to minus our force of friction times our displacement, my displacement is not equal to 3.28 meters, because that's what we just solved for in part A. So that's how long it took to come to a stop. But it's not asking how fast is it going at the end. We told you that it was 0. What I'm asking is how fast will this object be going once it leaves the spring? So my spring is compressed 0.3 meters. So if this is like my before picture, and then this is my after picture, I have my spring that is now stretched out, and it just left that spring. So it was here, now it's here, it has moved 0.3 meters. That's the delta x that my object has moved, because that's how far my spring was compressed. So my spring is going to push 0.3 meters, and then once it leaves that, it's not pushing anymore. But this is the delta x that we use in that equation. Let me get rid of a couple of this stuff from the earlier part. Okay? So when we talk about the work done by friction in our work in plus work done by friction is equal to the all expanded out stuff okay, something like that. Then what we can do is there's still no push, no apply force. There is work done by friction that we are going to use this number. Remember, it's not -90 because it is only moved 0.3, not the total distance. This time there is a kinetic energy at location 2. That's what I'm asking, is how fast is it going after it just leaves the spring? But it's a flat surface, but if it just left the spring, that means that spring is no longer compressed. Start at rest, no height, but there was a compressed spring to start from. Okay? Then we can solve for V2 within that KE2 piece. Hopefully that helps answer your question for that. If it doesn't, let me know.